Okay. So we used a relation on this. What is the relation? The relation was this: x1 by y1 or x1 by x2 is related to y1 by y2. He said if and only if x1 y2 equal to x2 y1. Remember the same thing relationship. If you replace this by less than, then you have x1 by x2 less than y1 by y2. If you replace this by greater than, you get greater than relation, and so on. Okay. Now this is a relation that you use. So you see that here 1 1 is related to 2 2 is related to 3 3 is related to 4 4 is related to n n, etc. So every lattice point on this line, originating from origin and then going all the way there, and if you have all these lattice points are related to common. Now if you take this point, what is it? It's actually 2 1. 2 1 is related to what? 4 2. 2 1 is related to 4 2, etc. Now if you see that the radial line that joins the origin with 2 1 passes through this, my the points are not properly marked, otherwise this straight line should pass through. As you know. And you see that 1 2 and 2 4 should have the same line passing through them, starting with the origin. Okay? And so on. So if you take some mn, you draw the line passing through that. It will pass through certain rational numbers. For instance, if you take m by n, then it will be related to k times m, k times n. Right? So these are related. So you can find the lattice. Therefore, you have these lines. The lattice points lying on these lines all are related through this. And if you have a point on a lattice point on this line and a lattice point on this line, they are not related also. Okay? So you have now classified all the lattice points. Now you can see that this brings in what is called a disjoint union of subcollections. Each subcollection is a set of related lattice points. Now that's the point that you have. Then we observed that they are all this relation that you have defined is an equivalence. It's an equivalence relation. What do you mean by that? It is reflexive. It is, what's the next property? It is symmetric. That is, we say that x is related to y. The relation is such that x is related to x for every x. X is related to y implies y is related to x. Then you call it symmetric. If x is related to y, and y is related to z implies x is related to z, then you say it is transitive. Okay. So a relation that is reflexive, symmetric and transitive is what you call an equivalence relation. So you can check that this is an equivalence relation. This relation is an equivalence relation. So what does it do? It does not partition. I mean, this is one of the theorems that you should look at. Take a non-empty set on which you induce a relation which is an equivalence relation, then you can show that it induces a partition. That's a very general theorem that you can do. So which in turn takes up all these, I am just quantitatively doing it. So it into disjoint classes. And the property is that if you take an element here, alpha, if you take an alpha 1 here, then alpha and alpha 1 are related. But if you take a beta here, then alpha and beta are not related. Okay? So all the elements which are of fractions, all the fractions that are related to one another used to this relation, they belong to one block. So you have different blocks coming up, right? That is what you call, say, 1 by this relation. M by n is related to km by k. K running through all natural numbers. Okay? Right? Now we define a new class. So the class Q plus. At that time, plus has no meaning there. I mean, it's just a symbol. Later you will see why I have put Q plus there. So with some insight, I have chosen the notation. Okay. The Q plus is the equivalence class of all elements in the partition induced by if you want a concrete picture of this, see, all the lattice points on each of these lines are what are called related. Okay. If you take any line that originates from that starts from the origin in this Cartesian picture and passing through some ordered pair of natural numbers, then all the other ordered pair of natural numbers that lie on that line is related to it through this equivalence relation. So you have these lattice points actually breaking up into disjoint union of subcollections. That's what you have. So this is the relation that we have. Then what we did was, we took, this was the notation that we used, took one fraction, say p x by y, and then put a bracket here, and which means the entire class of elements, and I defined addition x1 by x2 plus y1 by y2 I defined as, what is the definition? No, the addition rule was really funny. It was x1 y2 plus x2 y1 x2.
The second, I emphasize one point. So this is the ordered pair x1 y2 plus x2 y1 comma x2 y2. This is done in a very strange way. Okay. Now, what do you do? So you might ask, so I am now defining the addition of two blocks. One block here, another block here. I add, I get a new block. This is my plane. Okay. How do I do that? Pick an element from here, pick an element here, from here. There are fractions. You know how to add fractions. Add the fractions, and this fraction should lie, the sum should lie in some box. Search for that box, and that box will be designated as the sum of these two. Does it make sense? That's the problem. If it makes sense, provided irrespective of the representative fractions you choose from alpha and beta, you reach to the same block. So it is independent of the choice of these things. So there is some work to be done to conclude that this similarly, you can show that with this kind of relation, the product is defined in this block. This is also making sense. Okay, for the same reason. For instance, you have another x prime, x1 prime, x2 prime in the same block, and y1 prime, y2 prime in the same block. Then the product will be x1 prime, y1 prime, x2 prime, y2 prime. You are asking the question: is x1 y1 by x2 y2 related to x1 prime, y1 prime divided by x2 prime, y2 prime? Using this relation, you can verify that it is really true. Therefore, irrespective of the representative element that you choose to perform the computation, you always end up with the same sum, or the sum is properly defined, the product is properly defined. So also you can verify that this property would prevail. So if x1 by x2 is less than y1 by y2, and then irrespective of what representative you use to compute to check this property, it will be true. What do I mean by that? See, you have this relation, that is x1, the block, this is the order relation. So what you expect is this: if you choose x1 prime by x2 prime, y1 prime by y2 prime, then the same relation should hold with the prime. Okay, you can prove that this is. Therefore, you see that you can define addition, multiplication, and order relation on these equivalence classes properly, and these equivalence classes are what you call QS. Okay, and the addition has been automatically extended to it, well defined in a well defined fashion. So also multiplication, so also order relation. So all these things will come up from it. So you get the same kind of, whatever you have verified for fractions can be immediately translated to the set of rationals. The only difference is that, see, you say that when you work with the fractions, you write x1 by x2 is related to y2, you can only x1 y1. Okay. Whereas in the case of this is written as equality. Okay. So what further things you have? Is n in it? You look at the natural numbers and you take any n comma 1, or this is the same as n by 1. N by 1 is identified with the natural number for every n. Therefore, you see that every natural number can be discovered as a fraction, and therefore equivalently as a element of q plus. Or what you have is that n is contained in q plus. Not only that, see, the same rule of addition, that if you apply the rule of addition of two elements from here to those identified with n, then it just boils down to the sum. Because you see that, look at this is going to be x1 by 1, y1 by 1, so y2 and x2 are 1, therefore this is going to be x1 plus y1 divided by x2, y2 is going to be 1, so this is going to be identified with x1 plus y1. That's the sort of relationship that you have. Okay? That's the important part. Therefore, you see that structurally this has been embedded in Q plus. Okay? So we have enlarged the system to a class called Q plus. Okay? This is what we have. Okay, having got this, now you ask, do you get anything new out of it which n did not have? Or was it really worth doing all these exercises? Let us see. So let us, from fractions, we have gone to fractions. Okay? So I will just take out all these things and then write down. Just reach out to what is called fractions to this. Okay, fine. What are the consequences? Let's write down the observations that we make from that. So the first one is every natural number is a rational. That means to identify x is identified with this fraction. This includes 2x by 2, kx by k also. Okay. So that is that. The second one is that all these addition order and are consistently are pass over to q plus. Okay, so this is a very genuine extension of n. Note that also. Q plus. What is the meaning of this one? Suppose I have 2, I know 2 is less than 5. 2 by 1 is, or the block 2 by 1 is less than 5 by 1 also. So also I take 2 plus 3 equal to 5. The block 2 by 1 plus the block 3 by 1 will give you the block 5 by 1. Similarly about multiplication. Well, that's the meaning of the operations are completely respected, or in other words, it is a structural extension of this. 2. What do you have? One thing that really, one casualty that you have is nextness. Is no more true. So there is a difference. You cannot say that given a rational number, there is a rational number next to it. Why? If there is such a rational number to its right, then you see that in between there should be no rational numbers at all. But what you see is that if p is a rational number, q is a rational number, then p plus q by 2 has the property that this property is there. So if p is less than q, then p plus q by 2 lies between p and q. That means q cannot be the next to this. If you take two different rational numbers, there is always a rational number. So the nextness really goes away. Okay. You have, look at this one. Suppose you look at this equation. Suppose a comma b belongs to b plus. Then the equation has a unique solution for all a and b belonging to q plus. How does it come? Suppose I write a as a1 by a2, or I write this as, this is the fraction identified with it. B is the block corresponding to B1 by B2. Now the question that you are asking is this. See, Ax equal to b, does it have a solution? Can you find an x such that Ax is equal to b? This is the question that you are asking. So for fractions, so these are the representative fractions. So you have a1 by a2, and suppose you are taking x1 by x2, you are asking the question, can you find this equal to b1 by, does there exist x1 x2 x1 and x2 such that x1 by x2 a1 by a2 into x1 by x2 equals to this? What do you get? You take x1 by x2 as something like this, a2 b1 divided by a1 b2. Okay. Or in other words, you take x1 equal to a2 b1, x2 equal to a1 b2. Then you can prove that a1 by a2 into a2 b1 by a1 b2 will give you b1 by b2. That's it. So there exists such an x. So that is true for every x. Oh, sorry, for every choice of A and B. This is true. So this equation always has a solution. It's quite important here because this equation did not have a solution in all cases, or at least in some cases it failed to have a solution when you were in the set of natural numbers. For instance, if you take 2x equal to 3, there is no solution, no natural number x such that this is true. But when you work with what are called rational numbers, the same equation has always a solution. So we have got our one problem.